maintain for the rest of the year, or be maintained for the rest of the year. I want to talk about, they're called transformations. You guys remember in like geometry. So let's go back to geometry real quick. Let me give me a new graph here real quick. In geometry, I gave you like a graph like that or a picture like that. And I asked you, can you take that graph? Can you take every one of these ordered pairs? So let's say, view the algebra here. Let's go. All right, so I give you every one of those ordered pairs, and let me actually snap those to integers. And I say, okay, take that image and slide it to the right 3 units and slide it down 2 units. You remember doing that? Okay. And that gave, so if I slide it to the right 3 units, what coordinates are being impacted? The x-coordinates, right? Okay. So I'm going to have some x-coordinates. You know, one x-coordinate is going to be, if I take the 2, 4, and I slide it to the right 3 units, it's going to be 2 plus 3 gives me 5, right? Okay. And then if I take the y-coordinate, and I say move it down 2 units. So that point of 2, 4 is going to turn into 5, 2, right? So that point J is this point here, G, move 3 units to the right, 2 units down, right? Should I be able to do the same thing with this one? Move it 3 units right, 2 units down. So that's going to give me, what, 9, 1? And then this one should go 6, negative 3, right? I'm sorry, 6, negative 4. 6, negative 4. And now if I connect those as a polygon, okay, this graph here, this rectangle, or not rectangle, triangle, okay, has been moved to the right 3 units, and then down 2 units, and they match, right? Okay, those were referred to as a translation. A translation is left, right, up, and down movements. But collectively, those are called transformations. Okay, remember dilating them? Okay, basically multiplying everything by some constant and makes those points grow. We reduce them. Okay, we even did this. We said, let's take this series of points and reflect about a line. So let's say, I'm not sure how to do this. Select object to reflect, then line. Okay, so if I click that, and then I want to reflect across that axis, we did that, right? Okay, look at what happened to the ordered pairs. If I reflect across the x-axis, the x values all became negative, right? Okay, we could do the same thing, reflect across the y-axis, and now the ordered pairs, the y values just became negative, right? Or the opposite. Okay, so we've done that stuff, and that's really all we're going to do right now. But instead of doing it with geometric shapes, we're going to do it with curves. Okay, and what is nice is that if we understand how, with the geometry, how, you know, in that triangle, the 3 points were transformed. How they were transformed means to change, right? How those 3 points were changed. Okay. And that can help us get the new image. The same thing's going to happen when we talk about functions. We're going to want to know a series of points. Okay? And hopefully we have a good understanding of some points that are useful to us in this course for particular functions. I'm just going to start with x squared because I think it's maybe the easiest function to kind of gain this understanding with. So I'm going to type in, and I'll put this on my website so you guys can mess with it. It's not great yet. I'm going to adjust it a little bit before I put it on there. But I have this parabola x squared, right? Okay. And I just put a general formula here, ax squared. And you see down here that it's telling me right now that a is 1, right? And I'm able to adjust the A value, and then adjust the graph, correct? All right, so I want to real quick do something, so just bear with me. I'm going to put a series of vertical lines in here, just so I can start getting some ordered pairs that I like. So let's go intersect there, intersect there, intersect there. Now I'm going to hide those lines. Now I got those points. And the reason I did that is I want these points to be able to change. Okay? But right now, if I look at those points, are those the points that from earlier in the week or maybe last week and even back to Algebra 2 and Algebra 1, you've kind of memorized for that parent function x squared? Okay? So those are a series of points that are going to be useful for us. Okay? What are all these blue points? Give me one real quick second. I hid the lines. It didn't hide these blue points. There we go. All right. So those are the key points that we know from that parent function. Well, when I change, look at those points right now. When I change this value of a, okay, did those x values change? I go back from a being 1, okay, are the x values still 0, 1, 2, -1, -2? Yeah, still got 0, 1, -1, 2, -2. Still have those when I go to 3. Still have those when I go to 4. Okay, does that make sense to everybody? So the x values are not getting impacted here, right? But how are my parent function y values getting impacted? If they start off there and I go to 2, okay, they were 4, 1, and 0, right? Now they are 8, 2, and 0. Now they're 12, 3, and 0. So how are these y values being impacted by this number here that we use, this a value? Right now, our parent function, okay, let me just put our parent function in real quick, x squared, okay? So on that, you have the point 1, 1 right here where my cursor is, right? When I have 3x squared, 1, 1 jumps up to 1, 3, right? If I had 2, 4 on my parent function, which is right here where my cursor is, on 3x squared, we have 2, 12. So if I compare 2, 4 to 2, 12, isn't the 4, the y value, getting amplified by that amount? Okay, so it's getting multiplied by 3. So every time that I take a parent function, no matter what it is, in this case x squared could be linear, could be x cubed, could be whatever. It's taking the y values and it's multiplying the parent function y values, and it's multiplying by that number. Okay, so let's use a different function. Let's go. Maybe I go square root of x. Okay, so it looks like that, right? So some points that we have on there, they're not really nice points right now, but you can still see 1, 1, 2, comma, radical 2, okay, 0, 0. But if I start taking that a value, I got to put an a in here, so a times, okay, so put that a value out front, and now I make that a go to 2, okay, still have the order, the x values of 1 and 2, right? Those didn't change, okay, but if that a value goes to 2, watch that number and watch that number. Did they just double? Did they just triple? Okay? So when I multiply some function by a constant out front, okay? A lot of times called a scalar, okay? When I do that, it's just impacting the y values, how large they are, okay? And that's regardless of the type of function we deal with. Something that you guys aren't familiar with might be like the function 1 over x. 1 over x looks like that thing right there. And I've got some ordered pairs here, don't really care what they are, okay? But if I multiply 1 over x out in front by some a value, and I start changing that a value, look at those ordered pairs. We got a negative 1/2, a negative 1, a 1, and a 1/2 for my y values. When I change a to 2, they should go to negative 1, that should be negative 2, that should be positive 1, that should be positive 2, right? And that is exactly what happens when that goes to 2. When it goes to 3, okay, the 0.5 got multiplied by 3, so it gives me 1.5. Okay, the 1 got multiplied by 3, goes to 3. 0.5 went to 1.5. Okay. Is that doable for everybody? Does that make sense? Okay. Now, what we call that algebraically, graphically, we say that the graph is being stretched vertically. If we look at kind of the parent function, the most simple way of looking at this graph, and then look at 2x squared, look at 3x squared, does it look like somebody is taking, maybe you think about like putting a nail right there where my cursor is, and then put your hands on those 2 points, and then pull up. Is that what happens? Do you think visually that's pull up on those 2 points, negative 2, 4, and 2, 4, and that graph looks like that, now that curve will get skinnier, right? I like thinking about last think like either a rope or a jump rope, like a rubber band or something, and just hold it with your 2 hands. And that thing's going to be kind of parabolic in nature, right? Okay. But if I put my foot in the middle of it and then pull up, okay, is that rope or jump rope or whatever, is it going to look like it got skinnier? And that's what's happening here. Okay. When it looks like it's getting skinnier, it's most likely, and we can change this eventually, but it's most likely going to be a vertical shift a vertical stretch. That's what we call it. When you multiply by a number out front of the entire function, it's referred to as a vertical stretch. Okay. I think maybe the easier thing for people to recognize is this transformation. We'll leave A as 1. Let's add to this some B value. Okay, and right now you see my B value is stuck at 0. Okay, so look at your ordered pairs. Still negative 2, 4, 2, 4, 1, 1, 0, 0, negative 1, 1. But when I change that B value, it changed my graph, right? Okay, changed my function. Still got the same x values, right? But what happened to all those y values? They go from 4 to 5. They went from 1 to 2 and 0 to 1, right? So all I did, okay, when I add a 1 on the end of the whole function, it's just adding 1 to the y's, okay? And that moves, we call that a shift, okay? I'm notorious for misspelling that when I write tests. Forget the F a lot. But when I move that B value to 2, it shifted everything up 2 units, shifted up 3 units, shifted up 4 units. So it slid back to what we're doing with the triangles. It was we call it a translation, moving it left, right, up, and down. In this case, just up and down. If I move B to a negative value, B is negative, it just slides it down. Is that doable? Okay. So the hope is that we realize that we can, if I know 5 ordered pairs from that graph, and maybe eventually know maybe 5 ordered pairs from that graph, okay, and I start changing A values, and I start changing B values, I can understand how those parent graph ordered pairs adjust, and it then becomes very easy for me to develop that graph. Does that make sense? From knowing what that graph looked like. Okay. So adding something to the entire function, to the end of it, will get the thing to move up and down. The hard part that people struggle with is moving left and right. Okay? And what I want to do here real quick, let's just deal with the square root function. Okay, so we've got square root of x. Okay? I don't really care about the ordered pairs right now. But if I have the square root of x, notice that, if I put plus b on the end of that, okay, and I make my b value 1, 2, 3, does the same thing, moves it up and down, right? Okay? But what if I want to move it left and right? The place that I have to add something is to the x. Okay, so when I hit enter here, I want you to see where that b value goes. Because right now, notice I did it wrong. Right now the b value is on the outside, right? So I moved it up and down. Okay, but when I put that b value, simply a repositioning of my parenthesis, now we see that b value is actually underneath the radical, correct? Okay, so now when I make that b value grow, okay, it's a positive b value, which way does that take the graph? Left, okay? And here's the real. We should know this and be able to make the connection between this, because we've already done some stuff algebraically. Guess I'll write it on this so we can see it in the video. But we've already done some stuff algebraically to tell us that this should happen. If I have, right now, the square root of x plus 3, and I ask you what's its domain, okay, don't you take this x plus 3 and make it greater than or equal to 0? And then you say x for the domain has to be greater than or equal to negative 3. So negative 3 to infinity should be the x values that I see on my graph, right? Are those the x values that you see then on that right graph? Okay. So the plus 3, okay, and it's all because of the work that we have to do here. Now these things relate. When I add something to the x value, now hopefully you realize that if I were to give you like a t-chart of x's, let's just use just some easy ones for square roots: 0, 1, 4, and 9. Okay. What we're doing here, before I take the square root, I'm going to take this x value and add 3 to it. Then I'm going to take the square root. Does that make sense? So then it provides me my root 3 for my y value. Okay? I'm going to plug 1 in, add 3 to it, so I get 4. Then I take the square root and I get 2. Okay? So if you are adding something to the x or subtracting something to x, before you apply kind of the overarching or the dominating function to that graph, you are going to move something left and right. Okay? So if I deal with, let's go back to a square root function. Or not square root, a power function. Let's say I start with x squared. We know what that looks like. Okay? But now, if I write it so that I subtract a number, let's add a number, okay? Add a number to x before I square it, so it should end up getting me something like this. Does that make sense? Okay? You're adding 3 to x before you square something. So what's happening is that you are adjusting, you're altering just the x values. Notice if I go back to make b go to 0, okay, you just have x squared, right? Okay, but now if b goes to 1, you see how you still have the same y values. You have a y value here of 4, and a y value of 1, and a y value of 0. When I move this thing either direction, do I still have a y value of 1? Do I still have a y value disappeared, but I still have a y value there of 4, right? Okay. Y value over here of 4, you're seeing it. My line just isn't here anymore. But the y values don't change when I move it left and right. It's the x values that are altered when I move it left and right. And that's the algebra that's happening when we see addition or subtraction occurring before we take the overall kind of dominating function of the problem. But what is important that we understand is that when it's addition, you're actually moving graphically, it moves it to the left, which is maybe a little bit counterintuitive to what you would think, right? Most people think subtraction would go to left. With functions and translations, if you add to the x first, it moves it to the left. If I subtract a number, it moves it to the right. Okay, and we've done this. You guys remember we did this with circles, right? Okay, like x plus 3 squared plus y minus 2 squared equals 4. Okay, that moved the circle left, right, up, and down, opposite of what you thought it should have been. So if it was like x plus 4, it would have moved it left. If it was y minus 3, okay, it would have moved it up, right? Okay. So when you're subtracting from a variable, before you apply the overall function, you're moving it left and right. Okay. And if the variable is y for any reason, you would move it up and down. But right now, we're not going to see that. We're going to deal with those types of functions. What would happen? We didn't talk about this yet, but what if I did this? Let's say a times x is that, and I'm going to put another function in here. Let's say that g of x is equal to the opposite of a times x squared. Don't worry about that right now. Let's go back. B go to 0. I want this thing to be x squared. I didn't do what I wanted to do. Where'd G go? Algebra. There we go. All right, so right now we're comfortable with looking at that red curve, okay? That red curve when A is positive, right? Okay? But when A is negative, look what it does to that curve. Okay? Now, so that would be, this curve here would be just x squared. Does that make sense? So the black one is like the parent function. The black one would be 2x squared. The black one would be 3x squared. And the red one is negative x squared, negative 2x squared, negative 3x squared. Okay? You can kind of see the difference over here. Okay? The opposite of negative 3 would be positive 3, right? So the black one is positive x squared. This one's negative. Are they the same except for being reflected across the x-axis? That kind of makes sense? Okay? So, when you multiply a function, let's say I start with square root of x. Square root of x looks like that, right? Okay? If I were to take the square root of x and just multiply out in front by a negative, it reflects it over the x-axis. Is that doable? Okay. If I started with something like, I don't know, pi raised to the x. Looks like that. Well, if I multiplied it by a negative out front, just trying to show you functions maybe you haven't seen before, multiply it by a negative, still does the same thing. Reflects it over the x-axis. Does that make sense? Okay. Let's see what happens if I, just a location of the x, or the negative. If I go square root of x, looks like that. But now instead of multiplying the whole thing by the square root, what if I just multiply the x by a negative, do that first, and then take the square root? What axis do you flip over there? The y-axis. Okay? Same thing happens no matter what function you're dealing with. If I'm dealing with, I don't know, let's go the cubic. Okay? Think about what that's going to look like if you flip it over the y-axis. Would it look something like that? Okay? So I'm going to multiply the x by a negative before I cube it. And when I do that, it flips over the y-axis. Okay? Now this one's kind of unique because if I would have multiplied the entire function by a negative, So negative 1 times x cubed does the same thing, right? Okay. So that's a unique one where an x-axis reflection and a y-axis reflection develop the same curve. But if I just go like pi raised to the x again, okay, what that look like? Well, if I multiply the x by a negative first, see where the negative goes, it's going to reflect over what axis? The y-axis. Okay? So those are things that we want to talk about and think about throughout the rest of the year, is when I multiply the entire function by something, it's going to be a vertical stretch. Okay? It's going to change the y values, and we want to talk about how it changes the y values. When I add a number or subtract, when I say add a number, I'm incorporating subtraction too, adding a negative, right? That happens. So when I add a number to a function, it's going to move it up and down. Okay? I'm adding to the whole function. When I add to the x value, before I apply my real function, my overall function, it's going to move it left or right. If I add, it'll move it left, and if I subtract, it'll move it right. Okay? Then when I multiply the whole function by a negative all the way up front, it's going to reflect over the x-axis. When I multiply just the x by a negative, it's going to reflect it over the y-axis. Okay? And we'll talk about what we call horizontal stretches and horizontal compressions, but we're really not going to get into that and talk about that until we get into trig. It's easier to see with periodic functions that are doing the same thing over and over again forever. It's easier to see a stretch expression. We'll pick up with this again tomorrow.